Math 1325, we are going to be doing section 4.5 today. This is very similar to section 4.4 when we were doing derivatives of exponentials. So if you have a to the x power, well, let's actually even do this, a to the g of x power, then the derivative is itself. The derivative of an exponential is itself. And then you multiply by ln of the base a. Now, if the base a is e, then that part ends up equaling 1 and disappearing. But if it's anything other than e, then that'll be there. And then the chain rule always applies. You always, at the end, multiply by the derivative of the inside portion, or in this case, the exponent. So that gets attached to the end. Today, we're going to be doing derivatives of logarithmic functions, and logs are inverses of exponentials. So in essence, the first two steps are just backwards. If you have log base b of g of x, and you want to take the derivative of that, well, the exponential, in essence, what it is it's saying the same because you're really doing this over 1. So logs are opposite. You do 1 over the g of x function. Instead of being themselves over 1, they're 1 over themselves. And then instead of multiplying by ln of a, you multiply by 1 over ln of a. Or in this case, b, I guess, would be the base in this case. So ln of b. And then the same final rule is you multiply by the chain rule. The derivative of the original thing itself, if it's something other than 1, it just gets attached to the end. So just the first two parts, it's like here they're all multiplied together, and then when you put 1 over something, that's like you're dividing by it. So the first two steps get divided. And then if the base is e, which would be log base e, which is the same thing as ln, then you would have a 1 over ln of e right here, but ln of e equals 1, so then this part will be equal to 1, just like it is when this is ln of e. So my first problem in the 4.5 homework, y equals ln of 4 minus 7x. Whoops. That's weird. I was trying to click this. Okay, I was clicking stuff and other stuff was popping up. So number one, y equals ln of 4 minus 7x. So dy over dx, or y prime. First you do 1 over the stuff here. 1 over the stuff. Instead of just rewriting the stuff, it's 1 over it. And then you need 1 over ln of the base. In a ln, that base is e. And that equals 1 itself. So then this whole middle part's 1 and doesn't matter. Times the derivative of the inside. And this is just a linear expression. I could rewrite it negative 7x plus 4. So that way it looks like mx plus b. The derivative of mx plus b is just m. So times negative 7. And you always have this 1 right here. So usually when whatever's here, unless it's some complicated thing, it's just going to go times 1 and take the top of the final answer. So you end up with negative 7 over the 4 minus 7x. And these negative 7s don't cancel because this subtraction here prevents that from happening. You can only cancel individually if you're doing it through multiplication or division, not across pluses or minuses, addition or subtraction. So negative 7 over 4 minus 7x. Negative 7 over 4 minus 7x. Number 2, y equals ln of the square root of x plus 9. Y equals ln of the square root of x plus 9. Or you could rewrite that ln of x plus 9 to the 1/2 power. So if I'm going to write the 1 over part, the first step of the process, I might just leave the radical there because nothing usually happens to the denominator. So I'm going to write 1 over the radical part. That's the main rule for logs. The derivative of a log, you do 1 over what was originally there. In exponentials, you just do what's originally there, and then in logs, you do 1 over what's originally there. And then if you have anything other than ln, then you would have 1 over ln of whatever the base was. So here it's base e, and then this doesn't matter. Now, the derivative of this is hard to do as a radical, so that's why I want to think of it this way. So this would start off as a power rule, and you would do 1/2 times 1, which is 1/2. You would rewrite the base, and then decrease the exponent by 1, negative 1/2. And then that's kind of a chain rule in and of itself, but then here it comes again. Now I have an inside part that I could have a derivative of, and if it was anything other than 1, it would matter. But because this is linear, the slope of this is a 1, so technically you're chaining on another 1 there. So I was doing a chain rule inside this power rule right here just for doing the derivative of the original stuff. Okay, so then this 1 doesn't matter. This 1 wouldn't matter, except that the only other thing in the numerator is 1, and you can never have a blank top of a fraction. So 1 times 1 just makes the numerator 1. I can put this 2 in the bottom. And then this could not only go to the denominator and become 1 over, and I won't write the 1 anymore, x plus 9 to the 1/2. You can change this negative 1/2 to positive 1/2 if you move it down to the denominator. And then after it's in the denominator and it's positive 1/2, then you could do square root. And any square root times itself is just that stuff without the square root. That's a shortcut in algebra. That square root of 7 times square root of 7 equals regular 7. Square root of x times square root of x equals regular x. This is the basis for rationalizing denominators too. So the square root of x plus 9 times the square root of x plus 9 is just regular x plus 9. And you probably could leave the answer like this. You could distribute this and get 2x plus 18 if you'd rather have that. Maybe that's less typing to do that since that's so easy. I may as well go ahead and do that. 1 over 2x plus 18. And that way I don't have to write the parenthesis part. So it wouldn't be wrong if I left it 2 times x plus 9 though. Okay, so again, watch out on these because a lot of people get focused in on the rule that they're currently doing. In section 4 or 5, you're doing log rules and always looking for chain rules. But then old rules of the past can get forgotten. There's a negative 7x. That's not just a times, that's an x. Negative 7x times the natural log of 4x plus 3. I have 2 different functions of x multiplied together. So that's another rule in and of itself. Negative 7x times, they didn't write that, but there's a times there, ln of 4x plus 3. I've got a first function of x times a second function of x. This is the power rule. I'm sorry, the product rule. I'm multiplying product, 2 things involving x. If there was no x here, if this was just negative 7 times that, then it wouldn't be the product rule, because then you would just be doing a constant times it. So the derivative of the product rule is first times the derivative of the second. Here's where the new rule comes into play. So I want to do the derivative of the second just like I did the first 2 problems. So that would first be 1 over the stuff. And I'm going to put a parenthesis here because there's a bunch of stuff here. 1 over ln of the base, but this base is e. And then times the chain rule, which is 4. So this big parenthesis, this is still derivative of the second. Plus second times the derivative of the first. The first is a linear function, so the derivative of that is the slope in front, -7. 1 over ln of e equals 1, so that doesn't matter. So I could do the 4 times the -7 and get -28x over 4x plus 3. Okay, wait a minute, I was going to put a plus here from this, but then I realized, wait a minute, there's a -7 back here. So either plus a negative, or we could just simply write -7 ln of 4x plus 3 over 1, if you want to put over 1. So we've got 2 fractions subtracted, and I'm not sure if we just left it like this, would they take that answer maybe? Or are they going to force me to get a common denominator here? So I could get a common denominator if you just multiply the second fraction by 4x plus 3 over itself. And it isn't going to do a whole lot other than you could insert a 4x plus 3 right here. It's not going to affect the log part. So because it doesn't really help to simplify anything, I'm guessing that they would take this too, because it's not that much different than if I went ahead and did a common denominator. So let's, in the homework, you can always try that first, since if you get it wrong, you get another chance to do it. And that way you can learn what they want or not. It can get tricky sometimes, where sometimes they'll take different versions that don't seem fully simplified, and other times they get picky about it. So it just takes experience till you get it down to what do they want exactly. -28x over 4x plus 3. And then I'm not going to write this over 1 part. I'm just going to write the top of this, which will make it just seem like a separate thing. -7 ln ln of 4x plus 3, which was what the original parenthesis was. And do they take this? Yes, they did. So, and that's another thing too, is try it the first way always. And then if they say wrong, then that's either you made a mistake or they want more simplification to be done. But there is enough leeway. They're pretty good about leeway on how should you write the final answer. That's one nice thing here, at least. I did have a student emailing me about having an issue with ln. That when I type ln, maybe you notice it got bold, where the rest of the stuff isn't as dark. And I'm just literally hitting the letter L, like L as in lion, and the letter N as in Nancy, LN on a keyboard. So I don't know. It's the only time somebody's ever told me that they type ln and they're counting the answer wrong. And when he's doing it, it's not bolding the ln, so it's somehow not recognizing it as natural log. Maybe another thing you could try is type log instead of ln, log for log, and do a subscript base e. In fact, the next time it comes up, I'll try that and see if they take that answer. Because log base e is the same thing as ln. Okay, 3, we just did a product rule, so here comes a quotient rule. Just because it's a fraction doesn't make it the quotient rule. It's a quotient rule because there's a function of x in the top and the bottom. If either the top or the bottom didn't have an x at all, if it was just a constant or something else, then it wouldn't be the quotient rule. So product rule and quotient rule, you have to have x's in both parts. That's how to recognize it. So I've got 4ln. See, the top of this would not be a product rule because it's just 4. It's not 4x. 4 ln x plus 8. That's just all one thing because the 4 is a constant. And then x squared in the denominator. So the derivative of y with respect to x, I have to do the quotient rule here. Second times the derivative of the first, and this 4 just comes along for the ride. Constant, you can just write them down and then pretend they weren't even there and do the rest of the derivative. So now just do the derivative on this ln part, which is 1 over the stuff, and then technically times 1 over ln of e, which won't matter here. And then the derivative of the inside is just 1, so that doesn't matter either. So this was second times derivative of the first minus the first times the derivative of the second. And that's quadratic, but it's just a power rule. The derivative of x squared is 2 times 1, x to the 2 minus 1, so that's just 2x. All over the second squared. So that was the quotient rule. Again, to review that, second times derivative of the first minus first times derivative of the second over the second squared. Okay, so for this part right here, 4x squared times 1 is 4x squared over x plus 8. And then here I could combine the 2x with the 4 and get minus 8x. The ln part, you can't do anything with that, so you just put that in the back. And then the denominator is x to the 4th power because that's where you multiply exponents. X squared squared is when you multiply 2 times 2, although if you accidentally added it, you would seemingly get the same thing. Now, usually they don't like fractions inside of fractions, so having this fraction right here could be an issue. I guess we should try it and see, but I'm guessing they're going to count this one wrong. So they usually don't like fractions inside of fractions, so I have to put a separate fraction here in the top. The top of the fraction has another fraction, is usually frowned upon. So 4x squared over, just in that over box, x plus 8 minus 4x squared over x plus 8 minus 8x minus 8x ln. See how when I hit ln it bolds it? And then x plus 8, and I'm going to wait a minute on checking if it'll take log base e, just because I'm not sure if they're even going to take this answer. And then over x to the 4th in the actual denominator. So this is an equivalent answer, but they might not like this fraction right here. And when I check this, sometimes when you do that, it'll say, although your answer is equal to the correct answer, it's not in the correct form. Oh no, see, they took this. So then that saves some messy algebra. If I had to keep going, then what you would do is you would have to multiply this. Let me do it on the whiteboard. Right here, this part, you would have to multiply by an x plus 8 over an x plus 8. And that way, this x plus 8 would be the denominator of that fraction, because there's just a 1 right there. And then this x plus 8 would need to come here, and it could get messy to write it that way. 8x times x plus 8 times ln of x plus 8. It looks even weird too. And you could distribute this potentially, which would be another possible equivalent answer. So they probably would take this if you did it. It's just, that's what I always do, is check if they'll take a sooner answer that maybe you don't have to waste time doing a bunch of algebra. But other times they get picky, and they would I've seen this counted wrong in other textbooks, so that's why I'm not sure here. We just switched this edition of the textbook, so I'm not sure on some of the answers how they want them. So that's, even I'm learning, so I have to learn a new system whenever we switch to one. So That's what I do, is I just try it, and if they take it, okay, then I save myself a bunch of work. I didn't have to simplify that. But I've seen other textbooks where they're very picky about this. They don't like fractions inside of fractions. They'll say, although your answer is equivalent to the right answer, you haven't fully simplified it. So at least you guys, while you're watching these videos, you can watch me experiment with things like that, and then you'll know, okay, then you don't have to waste your time doing all that work, extra work for nothing. Okay, you remember the movie Inception with Leonardo DiCaprio, where there was a dream inside of a dream? Here's a log inside of a log. Number 5, ln of 12x. Now the reason for the absolute value is log has a positive domain only. Remember, the log graph goes like this, and it goes right through 1, 0 on the parent function anyway. But its domain is 0 to infinity. It never equals 0. It never equals negatives. In fact, there's a vertical asymptote at 0. So the domain of a log has to be positive. So one way to handle that is you put absolute value. If there's a bunch of stuff there where you're not sure if the stuff is positive itself. If the stuff itself is positive, then you don't need the absolute value. And sometimes they get around that by saying, let me go back to one where that was there. Well, I guess they don't say it, but what they usually do is they'll say that assume the variable is positive or something like that, but they're not even saying that here. So we could have been putting absolute value up to this point, but they were taking the answer without it. Okay, so natural log of 12x. Remember, when you're doing derivatives, you want to go kind of like the outside inward. Pretend that you can't see this clearly. Think of it like kind of blurry. I can't see what's here. All I see is log of something. There's log of something. So the derivative of that is 1 over whatever the something is, times 1 over ln of this base, which would be e, so that's going to disappear. Now times the derivative of this, which is another log in and of itself. So the derivative of this, if this was my entire problem right here, I would do 1 over this stuff. And then there'd be another 1 over ln of the base here, but this base is e too. And then you would have the chain rule finally when you get to this inner part. The derivative of 12x is just 12. These 1 over ln's of e's are all equal to 1 and don't matter if there's other stuff. This 12 cancels that 12 since there's no pluses or minuses in the way. So only thing left, we do have to have these two 1's equal a 1. You can't have a top of a fraction blank. The bottom of a fraction can be blank, but not the top. So I got to have a 1 in the top, and then I need an x and this in the bottom, and usually you put the regular x in front and the ln stuff in the back. So here, technically, there could be absolute value bars here, but I don't think you need them. But if we assume x is positive, then we don't need them, but they usually will say that in the directions, but here they're not. But since they wrote it here without absolute value, the innermost one, then I'm going to assume that's okay to write it that way too. So 1 over x. Now, so ln, for some reason somebody's having trouble. Watch when I type ln. See how it turns blacker? It gets bolder. And when this student is doing it, his is staying the same shade as these other things. And then it'll say the answer is wrong. And what he has is exactly the same as the right answer, except because the ln's not getting bolded, it's counting him wrong. So let's try log base e, because that's technically what ln is. And then the 12x. Will they take it this way? They should. Yeah, see? So I'm not going to say who the person is, but that person knows who they are if they're watching this video. So that's another thing to try, is try log base e, because that's literally what ln is. Maybe then it'll pick up what you're doing. Because he was having trouble answering things in both the previous section and this one because he couldn't type ln. Okay, here's the first time we don't have ln. Now we have regular log, common log this is called. Ln is natural log. Log is common log. Log, not ln. 17x. So if you ever see ln, that's actually log base e. If you ever just see log, that's log base 10. 10 is because us humans have 10 fingers is why. That's common. We count things on our fingers when we're little kids or when they first started doing math thousands of years ago. So that's why we have base 10 actually. So you go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and then you jump to 10. If you ever watch The Simpsons, all the characters in The Simpsons, Bart Simpson, Homer Simpson, they all have 8 fingers only because I guess the cartoon drawers, if they tried to draw hands with 4 fingers and a thumb, it would make their hands giant sized. Apparently, I'm guessing that's why. So they just do 3 fingers and a thumb, and most people don't pay attention to that. But if we humans had grown up or evolved over the centuries as 8-fingered beings instead of 10, we would use base 8. That would be natural for us. That would be the common thing to do. And you would go 0, 1, 2, 3, 4, 5, 6, 7, and then after that would be a 10. There would be no 8 or 9. It wouldn't even exist to us. Just the same way we go all the way to 9. So there's these things called base. You can do computers work in base 2, so they just have zeros and ones only. They never get to 2. Another interesting thing was I was at Lone Star College here. I used to teach classes. I was part-time at Lone Star and HCC, and I was teaching all in person. This was before the pandemic. And then I got a full-time job at HCC, and now I just teach part-time at Lone Star with online classes because I have full-time classes at HCC. But at Lone Star College, when I was there part-time in person, they brought a hypnotist in one day. This was at Lone Star College, Montgomery. And he hypnotized all these people. It was a whole hour show and hypnotized like 20 students and did all these funny things with them. But at the very end, he gave 3 students a post-hypnotic suggestion. And this one girl, he told her, for you, the number 2 doesn't exist. And then when he woke them up and he started asking them questions, there was key words he would say. In fact, there were 3 kids. One kid's key word was loan, another one was star, and the other one was college. So when he would say the magic word for that person, then that would trigger what they were told. The one kid was told that as soon as he hears loan, that he would need to turn his shirt around backwards. And then another kid was told, when you hear star, you take your 2 shoes off and put them on the other foot. And then finally the girl, when you hear college, the number 2 won't exist for you. So then he brings one up and he's like, okay, how are you doing here at school? And what's your major here at Lone Star College? And all of a sudden you see this kid turning his shirt around and the kid in the back switching his shoes. And the girl, you didn't really notice anything, but supposedly then the number 2 didn't exist for her anymore. So he brings her up and he's like, okay, I want you to count how many fingers you have on one hand. And she went 1, 3, 4, 5, 6. That somehow didn't bother her. And he's like, okay, 6 fingers on one hand. That's pretty interesting. So if you have 6 on one hand, then I want you to tell me how many fingers you have on both of your hands. So she's doing 6 plus 6 in her head, but she can't say 12 because 2 doesn't exist. So she just went to the next available number, 13, and that's exactly how bases that are less than 10 work. Base 8, you go 0, 1, 2, 3, 4, 5, 6, 7, and then you just jump to 10. There is no 8 or 9. So she says 13. And he's like, that's interesting. Go ahead and count it for me. So she's like 1, 3. See, even I messed it up. And so you wonder if this is all rehearsed, it could have been messed up easily, but she just very naturally went 1, 3, 4, 5, 6, 7, 8, 9, 10, 11. And then she was stuck and she had this weird look on her face like it was really hurting her brain. It was hurting her brain that it didn't come out to what she said it was supposed to be. And then the guy says to her, the hypnotist, he's like 13, or he's like 11. I thought you said it was going to be 13. And she's like, I did say 13. And it was really bothering her. It was like it was going to hurt her almost. And then he just kind of casually says, "Oh, so you're missing 2?" And she immediately said, "No, I'm missing 1." Which to her, that was right. From 13 back to 11, that's only 1 to her. There was no 12 for her. Now, I don't know what happens after the show. Does he correct this so she's not going to be in pain the rest of her life with this? But this is always what reminds me of that. Humans, for us, 10 is the natural thing here. Or I guess common thing is, this one's called natural log. Whoops, natural log. Because there's a lot of things in nature that use base E. But common log, it's the most common thing for humans is to count to 10, is why it's called that. So you have to know that there's a 10 here, is my point of this long story. So the derivative of this is like the other ones. You do 1 over the stuff first. Now here's the first time where I need to do 1 over ln of a base that's not E. So then I need to have ln of 10 right there. And then I needed to do the derivative of the inside stuff from the chain rule, which is just 17 since that's linear. And then this 17 could cancel that 17 since we don't have any pluses or minuses. So 1 times 1 is 1, and then I get x ln of 10. One over x ln of 10. So then we need that ln. When it's ln e, you don't put it because it equals 1, but ln of anything else. If you do e 2.71828, ln, here's log, here's common log, here's natural log. Maybe you can't see that off the screen there a little there. Here is common log, log, here's ln natural log. So I hit the E button first, 2.718281828 and so on. And then if I hit ln, it's going to say 1. ln of E equals 1. But ln of 10 is just a messy decimal. Doesn't equal anything special. Just like square root of 10 is a messy decimal. So logs of numbers that are not equal to their base, then you just get messy decimals, and that's why we don't do that. We leave ln of 10 in the answer because the messy decimal doesn't look nice and it's not exact. So they actually wrote the 10 this time on number 7, but normally that's left blank. Just like square root, you don't put the little 2 for square root, it's just understood. So the 10 is usually understood, just like in ln, the log base E is understood. It's not wrong if you write it, it's just much more common not to do that. So on 7, they went ahead and put the 10 anyway, so it's not wrong to do that, but you normally just leave that blank. They actually should have done that on 6 first and then maybe on 7, not done it just because it would have been better to see that it was there first and then to let you know that it's okay if it's not there. X squared plus 2x to the 11 halves power. So first I do 1 over all this stuff, just like it looks. You don't change it anyway. You just write it. Just like when you're doing exponential, you just write the whole stuff again. 1 over the stuff times 1 over ln, not log, but this is always ln, whether there's an ln here or not. ln of the base, this base is 10, so I need to have it. And then now this last part is whatever, like if you were back in section 5.1 or what chapter are we in, 4? Like all the way back in 4.1 is when you learned how to do something like this actually. Well, at least not the inside stuff, but the rest of it. So I just want to do the derivative of this. It's actually more like section 4.3 where you're doing the chain rule. So it's kind of like the power rule where you do 11 times the base, decrease the exponent by 1. 11 halves minus 1 is 11 halves minus 2 halves. That's 9 halves. But then the derivative of the inside, here's the chain rule again. Then 2x plus 2 is that derivative. Okay, so now one thing I'm looking at is I was thinking, should I factor out a 2 here? You don't have to, but I noticed that if you did, Since there's no plus or minus here or there, then you could cancel those 2's at least. So all that's left in the top is this x plus 1 and this 11. So I could either have 11 times x plus 1. Actually, this is in the top too. 11 times x plus 1, or you could distribute it and make it 11x plus 11 if you want. But I'll just leave it like that because we're going to also have this attached to it. And then in the bottom, I just have the ln of 10 and this in whatever order you want. Now, actually, see what's happening here is this is not even going to be the final answer, because now we have this that could divide and reduce. Those are the same base. So that's where you just subtract exponents. And if you ever have an algebra like x to the 9th over x to the 11th, let me do it without fractions first. X to the 9th over x to the 11th, you're technically doing x to the 9 minus 11. That's when you subtract exponents. That's x to the negative 2. But then you could make it 1 over x to the positive 2 using the negative exponent rule. So a shortcut that I like to do is if there's an 11 here and a 9 there, I just subtract them normally. 11 minus 9 is 2. And then you put the x to the 2 wherever the bigger one is. So in other words, say you had like an x to the 7 over an x to the 13. Instead of doing 7 minus 13 is negative 6, and okay, now let me change the negative back to positive. You can just say 13 minus 7 is 6, and I'm going to put it where the bigger one is. And it can be 1 over x to the 6 in one step instead of 2 steps. So 9 halves minus 11 halves is negative 2 halves, or if I did it backwards, 11 halves minus 9 halves is positive 2 halves, which is the same thing as 1. And then it would be in the bottom because the bigger one's in the bottom right now. So this cancels out that in essence, leaving just x squared plus 2x. And the ln of 10, obviously. And then there's a slight danger here. You don't have to pull a GCF out of here, but if you did, it would leave x plus 2. And if it left x plus 1, then you would have to cancel it with that x plus 1. So remember I said before, if you can factor and cancel in these problems that have denominator answers, then you have to do it. But if you factor and it doesn't cancel, then you could leave it unfactored. So there's going to be multiple versions of final answers here that would be equivalent. I could leave what I have right here. I could do this over this if I wanted to. I could distribute this 11 in and do it over either denominator. So there's a handful of different equivalent versions here, and it shouldn't matter which one we do. So fraction, in the numerator I have 11 times x plus 1 is all that's left. Or 11x plus 11 if you'd like that better. In the bottom, I can either factor out the x or not. Since it didn't help me to cancel, it doesn't matter. X squared plus 2x. X squared plus 2x ln of 10. Whoops. It's down in the denominator. Whoops. Okay. Oh, I see what happened is I was trying to hit a parenthesis, but it did a subscript somehow. ln of 10. And nothing else cancels or reduces, so then this should be one of the possible acceptable answers. But not the only possible acceptable answer either. So I didn't distribute this, but in essence I kind of distributed that one. Or vice versa. I factored out an 11 here and I didn't factor out the x here. That's okay. You could do either one or both or neither. Okay, here's a base 3. So different base for the first time. Log base 3 of 6 to the p minus 2. This should be an interesting problem. They're trying to hide a bunch of rules on one problem. Log base 3 but then in the parenthesis is 6 to the p, which is the previous section, section 4.4, minus 2. This is an exponential right here from section 4.4. But do the outside first. So I'm going to do a log rule first. So I have to do 1 over the stuff, just as it is, times 1 over ln of the log base, which is 3, ln of 3, and then times the derivative of this. That's the chain rule part. And that's last time's rule. So if you were doing the derivative of 6p in section 4.4, first you would get itself, then you'd multiply by ln of the base, and then you would do the derivative of the exponent if it was something other than 1, but this would have a derivative of 1. So technically times 1. And then you would move to the next term and do the derivative of that when it's added or subtracted, except the derivative of a constant is 0. So technically there's a minus 0 there too. Okay, so the minus 0 and the times 1 don't matter since there's other stuff there. Okay. I don't think anything cancels here. So 6 to the p, ln of 6, that would be the numerator. These ones wouldn't matter because there's other stuff there. And then the bottom would just be, I'll put it back in parentheses, 6 to the p minus 2, ln of 3. And ln of 6 and L divided by ln of 3, when it's going back to the rules of logs, 2 logs added can be 1 log multiplied. 2 logs subtracted can be 1 log divided, but 2 logs divided doesn't equal anything. And if you're ever unsure, you could say, it seems like maybe this equals ln of 2. Could this equal ln of 2 if I did an ln of 6 divided by an ln of 3, since 6 divided by 3 is 2? Does that equal ln of 2? Well, one way to tell is just check it on a calculator. What is ln of 2? ln of 2 is about 0.693. So if I took ln of 6 and divided ln of 3, does it equal 693 or not? ln of 6 divided by ln of 3 equals, see, it's not the same thing, 1.631. So these are not equal. That shows it doesn't work. So if you're ever in doubt, when you get an example like this, just try it. One quick example. If it doesn't work with one example can disprove something. One example can't prove that it's true, but it can disprove it. So that doesn't reduce. What it would take to reduce is you would have to have ln of 6 divided by 3. If there was just 1 log. 1 log divided is 2 logs subtracted. That's the property of logs that works. But 2 logs divided isn't, there is no property for that. So the top is 6 to the p times ln of 6. 6 raised to the p power ln of 6 over the 6 to the p minus 2, all in the parentheses because that's how it was originally. And then there was an ln of 3 down there with that after it, or in front of it if there's parentheses, but I usually put logs in the back because that way you know when the log ends. If you write ln 3, 6p minus 2 with or without parentheses, it might be questionable, is this all part of the log or does it just stop there? It's technically not part of it unless you put like brackets around the whole thing. But because there could be confusion about that, that's why I always put the logs in the back. Don't write ln of 6, 6 to the p. Don't flip-flop this because then somebody's going to wonder, is this all together right here or is that separate? You can put it in the front, but you have to put parentheses around it like that. That would be acceptable if you did that. So it's easier to type without parentheses, so that's why I put it in the back. Okay, we got two of these business problems remaining. The cost function for Q units of a certain item is C of Q equals 90Q plus 110. That's linear. Cost function is linear. The revenue function for the same item, R of Q, is 90Q plus 53Q over ln of Q. That's not linear. 3 parts. Find the marginal cost, find the profit function, find the profit from one more unit sold when 8 units are sold. Okay, marginal, anytime they say marginal anything, marginal cost, marginal revenue, marginal profits, that's a magic word for derivative, and I think we've talked about that before. So marginal cost means I have to take the derivative of this cost function. And since that one's linear, that's an extremely easy derivative. It's literally just the 90 slope in front of the Q. So the marginal cost is 90. Derivative is, if you remember when we first did derivatives, instantaneous rate of change. How is the cost changing at any given moment in time? This is saying that it's going up by 90 all the time. That's like they have to pay their employees, they have to pay their insurance, they have to pay their utilities. So it's going to cost the business this amount of money all the time, whether they do anything or not, if they make any sales or not. So the businesses always worry about their costs. They don't want their costs getting out of control. Okay, profit. Another thing businesses care about is profit. Profit is how much money do you take in, revenue, minus how much it costs you to do everything. So a profit function on number 9 for part B, part A was easy. Profit of Q always equals revenue of Q or X or whatever the variable is minus cost, the cost function. Profit is revenue minus cost. The revenue is a messy function, 90Q. Let me do it this way, 90Q plus 53Q over ln of Q. There's the revenue minus the cost. The cost function is this linear 90Q plus 110. And I'm putting parentheses around both of these because this negative goes to both of those. Negative 90Q and negative 110. And then this negative 90Q luckily cancels this positive 90Q because you're just subtracting that and getting 0. So the part B answer could possibly be this fraction minus 110 if they're okay with that not having common denominators, which earlier they were, so I'm assuming this will be an okay answer. 53Q over lnq minus 110. Yep. Okay, another way to describe a derivative in these business problems is marginal is the main way, but another kind of cue that you're doing a derivative is this idea that if you want to do one more unit sold, one more, so you're at a certain sales point, I've sold 8 of these things, what is it going to cost, or what is it going to profit, or what is it going to revenue out at if I do one more from where I'm already at, going one more on? That's instantaneous rate of change. What's going to happen if I instantaneously do another sale right now? So if you want to do it for one more from where you're already at, that's another way to say derivative. So they could have just said in part C, find the marginal profit, and it would have been easier to understand what they meant. But they're doing this as like, if you've already sold 8, what's it going to take you to get to that next sale after 8? Right there in that instantaneous moment of time. So find the profit for one more. So that means I got to take the derivative of this part B answer. This is the profit function, so the derivative of that will let me work with this part C then. So in part C, you're going to do the derivative of your profit function. And luckily, the second half of this subtracted part is a constant. So the derivative of a constant is 0. That part won't matter. So all I need is a derivative of this. And two things about it is a quotient rule because there's q's in both halves of the fraction. And there's even an ln in it. So whenever I get to that part, I'm going to have to use the log rule for derivatives. But think of it from afar. From afar, it just looks like a fraction if you can't make out the little individual details. And they both have q's, so that's when you have to do the quotient rule. So I'm going to do the quotient rule and do the second times the derivative of the first. And the derivative of the first is easy because that's linear. So the derivative of the first is just 53. Second times derivative of the first minus the first times the derivative of the second, and that's just a basic 1 over q, because the base is e here, so it would also be times 1 over ln of e, and then you would do the derivative of q, but that's equal to 1. So there are two more parts there, but they both equal 1, over the second squared. And then again, it could be an issue, although not so much here. I was going to say it could be an issue to have fractions inside of fractions, but they took one earlier that was okay. Plus here, it won't be an issue because this q can cancel that one. So ln q, I'm going to put the 53 in front of that, so it's clearly not part of the log. And then this part's just 53. And then I've got ln of q squared in the denominator. So they didn't ask for this answer, but they could have asked you at some point to find the derivative of the profit. But what they actually want is the derivative of the profit when 8 units are sold. In other words, the q equals 8. So once I got the derivative in general, then I'm going to do the derivative of 8. And if there was some messiness here that didn't reduce, I wouldn't even mess with it because you're going to be plugging 8 in anyway. So 53 ln of 8 minus 53 over ln of 8 squared. Now this one's complicated enough that if you're doing it with a simpler calculator, you would have to do that a lot slower, part by part, and write messy decimals down. But here's the nice thing about graphing calculator is I can do, if I do 53 ln 8 minus 53. You can handle all that at once. I don't know how well you can see that, but all I've typed is 53 ln 8 minus 53. That's the numerator. Whoops, I didn't close the parentheses, sorry. Okay, so 53, as soon as I hit ln, a parenthesis pops up. So after I type the 8, I need to close the parenthesis before I hit minus 53. So when I type it in my graphing calculator, a parenthesis pops up here, so I have to close that parenthesis. Because otherwise it was trying to do 8 minus 53, which is negative, and you can't do the log of a negative. So that's why I was getting an error message. So this is a messy decimal, but 57.2104017. The denominator would be ln 8 squared. 4.324077125. So if I divide that first answer, 57.2104071, divided by this current answer, then this should be the answer they're looking for because this is about money. So my calculator has 13.23. In other words, $13.23. So that's their instantaneous profit. They just made $13 a profit from that ninth after selling 8 and then instantaneously trying to go to the next one. Okay, so finally, this is similar. They want marginal revenue. They want the regular profit function. And then notice it does say marginal profit. So really, this part C is really the same thing as this part C, is just worded differently. But those both mean the same thing. So this makes it a little easier to understand. Marginal revenue, marginal profit, those are both derivatives, but part B is just a regular profit. So the revenue this time is not linear. Doing the derivative of that's not quite as easy as it was on number 9. The revenue function on 10, and they're back to the regular x's now instead of q's. R of x equals 30 ln 3x plus 1. So part A, marginal revenue is derivative of revenue. 30 is just a constant, so you can just write it down and pretend it's not there. Now do the derivative of the log part. And that rule is 1 over the stuff times 1 over ln of the base of the log, which here is e, times the derivative of the inside stuff, and that's linear, so then it would just be 3. And this 3, or even this 30, they do not reduce with this 3x because of the plus 1 right here. You're just kind of stuck with that. This part equals 1. This 1 won't matter since there's other stuff. So I can do 3 times 30 and get 90 over 3x plus 1. And everything else is gone. No way to simplify it. So the revenue, marginal revenue, is 90 divided by 3x plus 1. Okay, I didn't see this, but it says, how can the marginal revenue be found? Marginal revenue is the derivative of revenue. It's not subtracting. It's the derivative of R of x, yes. So they make you tell them what it is first before you give the answer. 90 over 3x plus 1. How can the profit function be found? See, this is good how they're doing this, because then you have to know when are you doing derivatives and when are you not doing derivatives. Profit is not a derivative. That's just regular P. But you also have to know from business that profit happens when you take your revenue minus your cost. So it's not the derivative of that. It's just finding the revenue minus the cost. C. It's not A. It's not find the derivatives of the subtraction. It's literally just the subtraction. Revenue minus cost, that's profit. Revenue is the money you take in. Cost is the money that goes out. Whatever is left is profit. So just do that. Take this ln and minus this, and I'm thinking it would just take it literally like that. 30 ln of 3x plus 1, that's the revenue function. No way to simplify it. Minus the cost function, which is literally just x over 3. Okay. And now find marginal profit when x is 90. So this is the same part C as the last problem. So I need to do the derivative of this, if you can see it. I need to do the derivative of this in general first, and then I can plug 90 into that. The marginal profit when x equals 90 can be found by evaluating marginal profits. We need P. It's this one, P prime of 90. So first I'll do P prime of x to figure out what it is, and then I'll plug the 90 in and do P prime of 90. Okay, and it does say round to the 10th, so then that means decimals are going to be okay at some point. So part B, the profit function, not derivative, but just regular profit function, was 30 ln 3x plus 1 minus x over 3. So part C, we need to do the derivative of that first, and then we'll plug 90 in after we get this. So we have a subtraction here, so we can just do these terms individually. The derivative of this is what this section's about. So first of all, you can ignore constants. Do the derivative of this, which is 1 over the stuff. It's in essence what I did right up here, actually. And this is 1, and then there's an extra 3 there. Minus the derivative of this. This is literally 1/3 x. X over 3 is 1/3 x. That's linear. So the derivative of that is 1/3. So I'm going to get if I needed to state what the derivative was, it would be 90 over 3x plus 1 like we had on part A. Whoops. Plus 1 minus 1/3, though. That's what's different about it, is it has an extra minus 1/3. So they didn't ask you to write this answer, but you basically have to find it in order to get to the answer they want. Now we can do p prime of 90 by putting a 90 right here where this 1x is. And the 90 in the question is just a coincidence compared to this 90 that happened to come from the derivative. So this is not me plugging in a 90 right there. But 3, here's where I'm plugging 90 in, plus 1, and then minus 1/3. And since they said round to the 10th, that's when decimals are okay. So, and this isn't too bad because 90 times 3 is 270, plus 1 is 271. So I have 90 over 271 minus 1 over 3. In a graphing calculator, you can just type that in all together like you'd read it out loud, and I think you can on the other calculator too. 90 divided by 271 minus 1 divided by 3, just like I read it out loud. And I got negative 0.00123000123. Okay, so the only thing I'm hesitating on is round to the 10th, but to the 10th it would be 0. Type in integer decimal, round to the 10th is needed. Okay, well, let's just see if it's 0. That's kind of weird, though. Huh. Okay, so that doesn't tell us a whole lot, though. But see, if you're rounding to the 10th, where did I have my answer? The 10th is the first decimal, and the next digit after that was 0, so then there was nothing to add. So it's literally negative 0.0. It's literally negative 0.0 to the 10th. But that's the same thing as negative 0, and there's actually no such thing as negative 0. It's just 0. 0 is an even number, but it's not even or odd. I mean, it's an even number, but it's not positive or negative. It's not positive or negative. So that's why I knew that if this was right, the answer was 0, but that was bothering me a little, that why would it be 0? Marginal profit. Okay, so that means your profit's not changing, I guess, is what 0 means. If your derivative of your profits is 0, the derivative is your instantaneous change at that moment. So your profit's not changing at all. Profit is negligible when producing fewer than 90 items. The revenue obtained after producing the 90th item is quite small. There is little cost to producing. There is no additional profit when producing one more item after the 90th item. So, see, that's that idea again. That derivative is the same thing as doing one more after the one you're on. That's kind of the instantaneous change. And there's no additional profit. 0, literally, no additional profit. So this is what a business would like to know this, because then they're just wasting their time if they make more than 90 items. If you make too many items, the issue is that can make the price go down. If the supply is high, the demand goes down. So there is a limit to what you want to make. You don't want to just keep making too much and have all this supply just sitting around. Okay, so that was bothering me at first, but yeah, that makes sense now that you see this. So that's like, don't go past the 90th item. Otherwise, you're not making any extra profits from doing that. So we have 100% on section 4.5 now. Save this. And we are now done with everything in the end of chapter 3. 3.3 and 3.4. And now we've done all chapter 4. 4.1 through 4.5. The next video will do the review for you. And then you got either Thursday, October 20th or Friday, October 21st to take your test. The test will appear right here on Thursday, October 20th. And then you have till Friday, 11:59 p.m. to get all the homework, the review, and the tests finished by. The next unit is here all now, so I've got 5-1 through 5-4, 6-1, 6-4, and 6-5. These are the only 7 sections we're doing next. We don't do 6-2, 6-3. I think there's even a 6-6 after that, so we just do the ones the school tells us to do. And then there's a review for that, and the test is already made. It's just it doesn't pop in until November 10th. And then we'll have one more unit after that, so that's what I'll be working on next. So you'll start seeing some other assignments popping in here soon as well, too. But that's another 4 weeks until we take this test. This test is another 4 weeks away, so plenty of time to get the other ones in there. See, we switched to a new textbook, so I had to recreate all the assignments from scratch, and it's just taking a long time. Okay, so that's it for this video, and I'll see you next time for the review for the second test.